And that brings us then to number 7. Dipoles. Whenever I see dipoles, I get a little nervous because in general that means a lot of mass. In this case, turns out that that's not so. I have here an x-axis, and here I have the y-axis. And here, at a distance a, y equals a, I have charge minus q, and at y equals minus a, I have plus q. And I want to know what the potential is at a point P, everywhere on the y-axis, here, 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 everywhere. Well, we'll take v equals 0 at infinity. Notice that v is also 0 here, because think about Walter Lewin with his plus 1 Coulomb coming from infinity. He has to do positive work to come to this one if he wants to reach this point. He has to do exactly the same amount of negative work due to this one if he wants to come to this point. The two cancel each other out, so it's clear that the potential is 0 here if I define the potential at infinity 0. Well, what now is the potential at that point P? It depends a little bit on where P is located. Whether the position of P is larger than A, or whether the position of P is smaller than A. And what I mean by that is it somewhere here, or is it outside there? I will assume that it is outside, and you will do the inside. If I assume that it is outside, then the potential at that point P, it's a scalar, is the sum of the potential due to this point and the sum of the potential due to this point. Let's first do this one. So that equals minus q divided by 4 pi epsilon 0. And now I have to take the distance between these 2 points, which we have called r earlier, and that is y, if y is the position of P, minus a. So y minus a. Plus, because this has a plus charge, plus q divided by 4 pi epsilon 0 times the distance from here to here. Now the distance from here to here equals a plus y. So we get y plus a. Well, you can massage this a little bit, and you can, following the instructions of your book, you can calculate, you can simplify it for y is much, much larger than a, and that will simplify matters, of course, enormously. I'm not going to do that. It's not all that difficult. But I want you to see that if, that's the part that you are going to do, that if point P lies below A, that the situation changes. Because when I now calculate the potential at point P to this charge minus q, the minus q remains here, the 4 pi epsilon 0 remains here, but now the distance between that point P and this position is no longer y minus a, but that position has now become a minus y. That is now the distance. And so this changes. However, this part does not change, because if I am here at a distance a below the y-axis, this is the y-axis and this is the x-axis, then this separation remains y plus a. So it's only this term that changes.